in
Russia.
Somerset.
Not Now that is a sight. So, Siberian tundra, very, very cold places are very, very good at preserving organic material. Organics are preserved to such an extent that in recent history there have been people called ivory miners which have actually dug up bits of the Siberian tundra to find piles of ivory tusks that prehistoric people used for building, etc. They had dumped them in the middle of their village, in the middle of the pile, and today people dig down into the permafrost to find these ancient villages, to find these piles, because the permafrost has preserved this organic material so well. And then they'll flog mammoth tusks. So, second-hand mammoth tusks because they've already been hunted, and it's quite incredible. But the DNA in this can be recovered, and it can be in incredibly good condition. As I'll go into a little bit later, DNA is a very fickle molecule. If you leave it too long, it dissolves. If you put too much heat into it, it'll dissolve. If you drop it, it'll probably dissolve. DNA doesn't like to hang around for very long at all.
Okay, slight exaggeration at the end there.
Just a small...
I drop my samples all the time.
I mean, I've fallen over and I haven't dissolved, so we good. But to the extent we've extracted some of their DNA, mammoth DNA, we know what colour they were from a gene called the MCO1R gene. They weren't orange or gingery through popular culture as they've been portrayed. And actually what you see on a frozen mammoth, they look like they died yesterday. They are really, really well preserved. But they're not orange or gingery. They are very, very deep chestnut or black in their
Oh, fantastic.
colour
Manny the
coating.
Mammoth from Ice Age was deep chestnut.
Hey, so again, that's actually true. Yeah. Well, they nailed that one. And there was a mutant type as well, which they've discovered, which is almost platinum blonde.
Wow.
So platinum blonde mammoths wandering around. And we know they were well adapted for the Ice Age. We know why they were able to live there. A Canadian scientist has extracted the DNA and found the correct genes, comparing them to an elephant's. And then he managed to reconstruct mammoth hemoglobin.
Wow, okay.
Which I think is incredible. So he looked at the genes necessary, he formed the proteins necessary, and hemoglobin is the molecule which sits in red blood cells, which takes on oxygen to transport around the body. It behaves incredibly differently to elephant hemoglobin, far more so as they are literally sister taxon. They are next to each other on the tree of life, the elephant and the mammoth. Normally at low temperatures, hemoglobin isn't amazing. It doesn't function great, but the mammoth hemoglobin excels at releasing oxygen at low temperatures. It's perfect for running around the tundra. Also, there's a gene called TRPV3. It's responsible for temperature sensing. And mammoths had extremely high tolerances to very low temperatures, and it's predicted that they just wouldn't really feel the cold.
So they had no idea.
And they've brought that back, these proteins, in labs, which is amazing, gives us a unique scientific opportunity to look at the science behind the adaptations of these incredible animals. And I'm telling you about these genes because we have taken the DNA from a long extinct animal and built them in a lab. We've built these proteins in a lab. We've done that. But what about bringing back an entire animal? It's a different kettle of fish entirely.
It sounds like you've got a lot of the advantages that you would get from de-extinction just from creating the proteins of the genes that you know already existed.
Scientifically, absolutely.
However, you wouldn't really get that systems biology response because everything's different. If you look at a gene on its own, it will probably behave completely differently to what you expected when it's an entire organism.
Absolutely. And also,
that's very interesting that they've done that.
Combining that with behaviour, how did they use it, in what way was it adapted? And yeah, I mean, it's even gone to the extent there's a mummified individual, a baby was found. It looked like it fell down after being attacked by some sort of large cat. This was a baby that they named Dima in 1977.
It's a lovely name.
Which is quite sweet. Yucca was another female juvenile that they found so well preserved that her hair was still fluffy.
If you have two pets that need naming, Dima and Yucca are gorgeous names after two mammoths.
They are absolutely fantastic. Two baby mammoths, yeah. So Yucca had fallen in, it looked like she had fallen into a pond. And into a freezing pond, probably died very quickly, and then froze. But with this incredible way of preservation, we know that she had a curly, dark brown coat, slightly fluffy, almost like it was just blow-dried. And her brain was preserved down to the neuron.
What?
It was that detailed. Russian scientists took out her brain to have a look at it, and it was preserved to the neuron.
The neurons are the cells that are responsible for transmitting signals around your body from the external up to your brain, so you know what's going on. So to be preserved down to the neuron. Incredible.
So from these discoveries, we know how their physiology in terms of their blood worked. We know what their diet is. We know the measurements. We know, even to the extent of the behaviours, we know what the babies were doing. We know how long they suckled for. So all that remains would be seeing all of these different aspects come together in the organism itself, in this majestic animal that might walk again. I mean, an animal that was still kicking 4,000 years ago when humans were building pyramids in Egypt. So it's really interesting. You can do all of these different sections, but putting them together would be another thing entirely. So there are 3 current ways to build a mammoth.
How to Build a Mammoth by Darwin's Black Book.
The first way to build your mammoth. So the first way to make your mammoth: take an Asian elephant egg, remove the nucleus from said egg, and replace it with the nucleus, or the genetic material, from a woolly mammoth cell.
Okay.
Then you put it into an elephant, and then you trigger it to stimulate it to start dividing. And now some months later, you'll have a calf developing with a woolly mammoth genome. It'll have a slightly different fetal development because you have put it inside an elephant.
Maternal effects, yes.
Yep, but you would have a mammoth baby developing.
That's kind of a similar process to what they did with Dolly the sheep in the 90s when they cloned an extant animal.
Yeah, so it's the same. Actually, one of the issues, though, how difficult it is with cloning, how difficult it is with just something of the same species. So putting a species thousands of years old in a modern day species, that's just asking for trouble. But yeah, doesn't matter because we don't actually have enough DNA to direct the production of an embryo anyway.
Oh, okay, so what else could we...
Yeah, that doesn't work. Right. Number 2 to how to build your mammoth. Artificial inseminate an elephant with mammoth sperm.
We have mammoth sperm?
Yeah, yes, because we've extracted it from, frankly, massive mammoth testes.
That's not what I... Okay.
Everything's frozen and broken because sperm only survives being frozen for about 15 years and then it just starts desiccating, and even if you rethaw it, it's just not viable at all. So yeah, you inseminate the elephant with mammoth sperm, and therefore...
So that would be elephant egg, mammoth sperm?
Yep. And
okay.
Therefore you'd kind of get a hybrid that would be born. And then you keep doing that over several generations and you'll slowly get a more mammoth animal, a more mammoth hybrid. It won't be pure, but after several generations, it'll get...
More mammoth-y.
More mammoth-y. But again, we don't have sperm because it's ruined, because it wasn't 15 years ago that mammoths were kicking, it was 4,000.
Okay, so that doesn't work either. What else can we do?
So option 3 for bringing back the mammoths. We know enough about some aspects, well, most aspects of the mammoth genome to take the elephant genome itself, replace sections of the elephant genome with mammoth genome, and this has actually started to be done in a lab. They managed to replace a specific section of the elephant genome with the cold-resistant genes of the mammoth. So they actually altered the elephant DNA to have some mammoth DNA in it to make it more resistant to the cold so it can live in tundra regions, because elephants in tundra doesn't really work. But that's, again, in a lab. They haven't done it full scale in an egg. But they are planning to kind of look at how to how to make smaller external ears, put subcutaneous fat in, change the hemoglobin to make mammoth hemoglobin as opposed to the elephant hemoglobin, then make it grow hair, etc. And you build, using the structure of an elephant genome, you build what you know a mammoth is into that. And that's the most viable option.
Okay.
So you use the structure of an elephant genome and then change it with what you know a mammoth is. So, why would this be a good idea? Why would anyone want to do this? There are a few benefits, and cast your mind back to a mere million years ago, where the grassy steppe was the most expansive ecosystem on Earth. It ranged from France to the coasts of China, all across Europe and Asia. It hung around for more than a million years, had ice sheets rolling around, carving out new valleys and making dramatic landscapes. But in Siberia, up in the north, the grassy steppe lay open, with underground water sources to feed the grass, and it was an incredibly productive environment. You had wild horses, you had ox, you had extinct types of deer, you've got mammoths. Now, grazers are incredibly important in a grassy environment. They maintain the grass. They eat the grass grows more, they fertilise the grass. There is an underground water source to feed said grass. It's a self-sustaining environment as long as the grass is trampled, eaten, and fertilised.
Okay.
Because what that does, it keeps the grass in check, and it makes sure that nothing else, like trees or moss, start to appear. The temperatures back then were similar to what they are today. So what we would see as the snowy tundra was just snowy grasslands. It was exactly the same. Mammoths agitated the soil. They had a huge amount to do with uprooting mosses and things from settling. So when they disappeared 10,000 years ago, we see a dramatic change in the environment. Moss took over. Moss settles, waterlogs the soil, the grass goes away, and now you've got a waterlogged, frozen soil that is so much less productive.
I see.
Because the mammoths disappeared. They were, engineers. They're maintaining their ecosystem. So when I said earlier about why they went extinct, there just physically weren't enough of them to maintain that environment for themselves. Projects at the moment are involved with bringing back similar species to what existed. So wild horses as well as oxen as well. And
it's a kind of more of a reintroduction than a de-extinction
absolutely.
approach.
Just to try and create something which has been affectionately termed Pleistocene Park. To try and create an environment, a very ancient, very productive environment, which was ruined effectively by humans 10,000 years ago. This is being run by Sergei Zimok. He's a Russian ecologist and director of the Northeast Science Station in Chersky. Sorry if I mispronounced that. And his idea of Pleistocene Park says, again, it could repair this environment. He has a big section, 160 kilometres squared, of grassy plains with increased grass growth. That's incredibly hard to say. So they can't go too far north at the moment because it's frozen. But this grassy plains, they've already introduced the Yucatea horse, and they really want to do it with a mammoth. They really want to introduce these huge animals to try and roam around, bring back an ecosystem.
I can see the benefits in that, yeah. That's definitely a good argument.
And it goes further. The ecosystem that the mammoths created could store a carbon content of 2.5%.
Ooh.
Which is 2.5 times more than all of the jungles today. And that in total,
a big plus.
It is, and it could store 500 gigatons of carbon.
So it could be kind of a response to climate change, bringing back the mammoths.
Exactly. We know that at the moment the climate is subtly different, but not huge amounts different since the Pleistocene. It hasn't changed dramatically, which means the mammoths would still be fine. It's still within the temperature range. And we would be storing a huge amount of carbon. And also, it would as the permafrost is melting with climate change, which is a very, very serious issue, huge amounts of carbon and carbon dioxide are about to be released. This will enable